Buenas tardes y bienvenidos al Museu de les Ciències. Mi nombre es Vicente Pelejero y pertenezco al Departamento de Divulgación de la Ciutat de les Arts y les Ciències. Y me gustaría agradecer especialmente la presencia de Carlos Emergildo, vicerrector de investigación de la Universitat de València, José Pío Beltrán, coordinador institucional del CSIC en la Comunidad Valenciana, Carmen García, coordinadora del área de físicas del CSIC, y a Javier Quesada, presidente de la Fundación Valenciana de Estudios Avanzados, que gestiona los premios Jaume I. En primer lugar, me gustaría destacar la intensa colaboración que mantenemos con el Instituto de Física Corpuscular de Valencia, que es un centro mixto formado por el Consejo Superior de Investigaciones Científicas y la Universitat de Valencia. Y gracias a esta colaboración, la Ciutat de les Arts y les Ciències se transforma en un puente que pone en contacto la divulgación científica de primer nivel con los ciudadanos de la Comunidad Valenciana. Y qué mejor forma de hacerlo que acercar la ciencia al gran público de la mano de sus protagonistas. Para esta institución a la que represento es un honor y un placer contar con la presencia del doctor Barish, Premio Nobel de Física por sus contribuciones decisivas al detector LIGO y la observación de ondas gravitacionales. Y aunque no quiero alargarme en mi intervención, no quiero dejar pasar la oportunidad de comentar que la ciencia ha alcanzado unos límites que en ocasiones roza la ciencia ficción. Y como comprobarán a continuación, la detección de las ondas gravitacionales ha supuesto un desafío tal que hasta el propio Albert Einstein pensaba que era imposible detectarlas. Tal ha sido el reto que hemos tardado 100 años en detectarlas, gracias al excelente trabajo de cientos de científicos e ingenieros de la talla del doctor Barish, entre los que también se encuentran investigadores españoles. Gracias a todos ellos, la ciencia ficción se transforma en ciencia básica que abre las puertas a multitud de aplicaciones, como por ejemplo la astronomía gravitacional. Me gustaría dar la palabra al doctor Juan José Hernández, director del IFIC.
Buenas tardes. Quisiera, para empezar, porque eso me ayudará a introducirle la historia científica del profesor Barish, a explicarles cuál es la relación del profesor Barish con nuestro instituto. No tiene nada que ver con las ondas gravitacionales. En nuestro instituto hay un grupo de investigación que está trabajando en el próximo acelerador de partículas que se llama el ILC, el colisionador lineal internacional, ¿de acuerdo? Es muy probable que las autoridades japonesas en unos meses decidan si será Japón el país que albergará ese acelerador lineal que involucrará a toda la comunidad de física de partículas. Para ello, nuestros investigadores y alrededor del mundo han estado trabajando más de una década en diseñar ese proyecto. En particular, en el instituto el proyecto está liderado por Juan Fuster y Marcel Vos, y ha habido un esfuerzo que es, como se llama, internacional para diseñarlo. Y ese esfuerzo ha sido liderado por el profesor Barish. Y esto me permite introducirle ese acelerador, por cierto, complementará al que está actualmente funcionando en el Laboratorio Europeo de Física de Partículas, el CERN, el LHC. Y eso me permite introducirlos en lo que se ha venido llamando gran ciencia. Se trata de enormes instrumentos científicos que están en la vanguardia de la tecnología de su tiempo, de alguna manera aprovechando todo lo que tecnológicamente es posible aprovechar, que involucra a ya no cientos, sino miles de científicos e ingenieros, que son costosísimos hasta el punto de que un solo país no puede permitírselo, y que finalmente, entre su concepción, el diseño técnico detallado, su construcción y puesta a punto y la época de explotación científica pasan décadas. Por ejemplo, en el gran colisionador de hadrones del CERN se empezó a pensar en él en los años 80 y es probable que dure más de la mitad de este siglo. Es decir, va a ser más de medio siglo de un proyecto científico. Y eso me permite describirles la carrera del profesor Barish en un momento que fue crítico precisamente para el detector LIGO. A finales de los años 80, a principios de los 90 del siglo pasado, Estados Unidos tenía un proyecto de acelerador que se llamaba el supercolisionador superconductor, o SSC. Iba a ser una máquina muy parecida al LHC, pero que iba a tener 3 veces la energía que consigue el LHC, es decir, alcanzaría 40 teraelectronvoltios. El proyecto, en particular, uno de sus detectores, GEM, estaba liderado por el profesor Barish. Debido a cuestiones que se han analizado históricamente, el caso, en particular por la oposición de una parte de los físicos de partículas, el proyecto sufrió muchas vicisitudes y en otoño de 1993 el Congreso de los Estados Unidos canceló el proyecto. Se habían gastado hasta entonces 2.000 millones de dólares, pero el Congreso decidió cancelarlo. Fue, por supuesto, un caos para la comunidad de física de partículas, fue un golpe durísimo para todos ellos, una suerte para Europa, porque pudimos traer un montón de inteligencia y de físicos brillantes de Estados Unidos, pero fue un golpe tremendo. Déjeme contarle una historia paralela. Algún tiempo después de la formulación de la teoría general de la relatividad, se empezó a discutir si ésta predecía ondas gravitacionales, es decir, ondas en las que lo que de alguna manera vibraba era el propio espacio-tiempo. Se convino que sí, que la teoría general de la relatividad las predecía, pero estamos hablando de los años 20 o 30, se dio por descartado que se pudiesen detectar, porque incluso con los fenómenos gravitatorios más violentos, esas pequeñas vibraciones eran tan minúsculas que era imposible de detectar. Allá por los años 70 del pasado siglo empezaron a darse cuenta los físicos que la tecnología de interferometría láser, que les explicará el profesor Barish, quizá podía ser la solución para detectar esas ondas gravitacionales. Finales de esos años, 2 institutos de tecnología de Estados Unidos, Caltech, el Instituto de Tecnología de California, y el MIT, el de Massachusetts, se unieron para hacer investigación y desarrollo en estas técnicas de interferometría para la detección de ondas gravitacionales. Y consiguieron que la Fundación Nacional para la Ciencia de Estados Unidos les financiase ese proyecto. Todo iba bien hasta que, digamos, finales de los años 80, incluso cuando la NSF, esa agencia financiadora, dijo que era muy interesante y que lo iba a financiar, lo cierto es que el proyecto, que ya se llamaba LIGO, entró en crisis. Ellos no lo sabían por qué, pero nosotros históricamente sabemos por qué entraron en crisis. El proyecto LIGO entraba en el mundo de la gran ciencia y no estaban preparados para afrontar ese reto. La física de partículas conocía la gran ciencia y lo que había que hacer desde hacía al menos 2 décadas antes. De tal manera que allá por unos años antes justamente de que se canceló el SSC, llegaron 2 informes muy negativos a la NSF sobre el progreso del LIGO. Básicamente los informes decían que en los últimos años no se estaba avanzando nada, en absoluto. Hubo una crisis enorme, hubo dimisiones, los institutos se reunieron para ver quién podría tomar a su mando ese proyecto y decidieron que la persona adecuada era el profesor Barish. Esto había coincidido, lo que había sido un durísimo golpe para la física de partículas, era una suerte para la detección de ondas gravitacionales. Era la persona adecuada en el momento adecuado. El profesor Barish, que ya tenía experiencia en dirigir grandes colaboraciones, puso orden. Por ejemplo, empezó a hacer algo que para los físicos de partículas es evidente, distinguió lo que era el laboratorio de la colaboración, empezó a hacer programas de desarrollo de las tecnologías que él sabía que deberían de utilizarse y captó, incluso desde la propia gente que había trabajado en el SSC, a gente tecnológicamente muy brillante. Todo el mundo está de acuerdo en que, de no ser por el profesor Barish, no sabemos si hubiese habido detección de ondas gravitacionales, pero desde luego se hubiese retrasado esa detección al menos un par de décadas. Algunos de ustedes pueden pensar, bueno, pero esto es pura gestión de personal o dirección de recursos humanos. En absoluto, no lo es. Un líder o los líderes de un gran proyecto de ciencia no solo pueden tener cualidades de libros de autoayuda de un gestor de una empresa, no. Son verdaderos científicos que saben la ciencia que quiere hacer el instrumento, pero también la tecnología que existe o que puede existir en un intervalo de tiempo razonable para llevarlo a cabo. Desde que el profesor Barish tomó en sus manos el experimento LIGO en 1994, habrían de pasar todavía otras 2 décadas más hasta la detección en 2015 de las ondas gravitacionales. Pero todo el mundo está de acuerdo que quien guió el barco en la dirección correcta fue el profesor Barish. Es por eso que merecidamente se le ha otorgado el Premio Nobel de Física 2017 y el Premio Princesa de Asturias también de ese mismo año. Bueno, y esa era la introducción que quería hacer del profesor Barish. Le paso la palabra al profesor Antonio Font, del Departamento de Astronomía y Astrofísica de la Universidad de Valencia.
Buenas tardes, gracias Juanjo. Como ya ha comentado el director del IFIC, el papel jugado por el profesor Barish en el éxito del Observatorio LIGO, el detector de ondas gravitatorias por interferometría láser, a mediados de los años 90, pues fue fundamental. Estos detectores lo que hacen es analizar, detectar, observar las ondas gravitatorias, analizando las franjas de interferencia que se produce en la superposición de 2 haces de un rayo láser en un interferómetro kilométrico Michelson-Morley con cavidades ópticas Fabry-Perot. El profesor Barish gestionó la propuesta científica del diseño de un detector basado en interferometría láser actualizable en el tiempo, de forma que se pudieran incorporar mejoras tecnológicas que paulatinamente aumentarán la extraordinaria sensibilidad que necesitan estos aparatos para finalmente conseguir la detección, empezando con el detector LIGO inicial hasta el detector LIGO avanzado, proyecto que inició sus observaciones científicas el 18 de septiembre del año 2015, en el llamado Observing Run número 1. Durante esa campaña de observación se detectaron ondas gravitatorias procedentes de la fusión de la colisión de 2 agujeros negros en 2 sistemas binarios, GW150914 y GW151226. Son 2 descubrimientos sin duda históricos que confirmaron la teoría de la relatividad general de Albert Einstein en un régimen donde todavía no había sido confirmada, que es el régimen de la gravedad intensa. Y además, como subproducto, también confirmó la existencia de los propios agujeros negros. Esta observación, como ya ha dicho el director del IFIC, fue merecedora de muy importantes premios internacionales. La segunda campaña de observación de estos detectores LIGO avanzados comenzó en noviembre de 2016 y terminó el 25 de agosto de 2017. Desde el 1 de agosto de 2017 hasta el final de la campaña, a los 2 detectores LIGO se les unió un tercer detector, el detector europeo Advanced Virgo, y con eso teníamos ya una red de 3 detectores interferométricos. La presencia de Virgo resultó ser muy importante, pues con una red operativa de 3 detectores se consigue mejorar significativamente la localización espacial en el cielo de las fuentes que emiten las ondas gravitacionales, respecto al caso de disponer tan solo de 2 detectores. Durante esas 3 increíbles semanas del mes de agosto del año pasado, los detectores avanzados LIGO y Virgo observaron conjuntamente ondas gravitatorias de un nuevo sistema de agujeros negros, GW170814, y por primera vez de la colisión procedente de 2 estrellas de neutrones en un sistema binario, GW170817. Al contrario que ocurre en el caso de los agujeros negros, que son soluciones de vacío de las ecuaciones de Einstein, en la colisión de 2 estrellas de neutrones también se produce radiación electromagnética en todo el espectro electromagnético. Y esta radiación pues, fue observada por casi un centenar de telescopios terrestres y espaciales en todo el rango del espectro electromagnético. y también impulsó la búsqueda de neutrinos por los correspondientes telescopios de neutrinos. Este fue un esfuerzo internacional sin precedentes que ha significado el comienzo de lo que se conoce como la astronomía de multimensajeros, y tan solo con una única detección ya ha permitido confirmar un buen número de predicciones teóricas fundamentales en el campo de la astrofísica relativista, como nos explicará el profesor Barish en su conferencia. Para terminar esta breve introducción, me gustaría señalar el importante papel que juegan los grupos españoles en este campo emergente de la astronomía de ondas gravitatorias. Por un lado, el grupo de la Universitat de les Illes Balears, liderado por la doctora Alicia Sintes, es miembro desde hace muchos años de la LIGO Scientific Collaboration. El grupo de la Universidad de Valencia, liderado por un servidor y con investigadores de dos departamentos, el Departamento de Astronomía y Astrofísica y el Departamento de Matemáticas, es miembro de la Virgo Collaboration. Ambos grupos participan en el desarrollo de software para la detección de diferentes tipos de fuentes astrofísicas de ondas gravitatorias, tales como fuentes continuas, púlsares, en particular el grupo de las Islas Baleares es especialista en la búsqueda de ondas gravitatorias de púlsares, o fuentes transitorias como binarias de agujeros negros, binarias de estrellas de neutrones, supernovas y estallidos de rayos gamma. Además de realizar investigación en análisis de datos y estimación de parámetros astrofísicos de dichas fuentes. El interés en este campo de la astronomía ha aumentado considerablemente en los últimos meses y hay dos nuevos grupos españoles interesados en unirse a estas colaboraciones. Uno en la Universidad de Santiago de Compostela, que quiere unirse a la colaboración científica LIGO, y otro en la Universidad de Barcelona. Además, España también participa en el estudio de los detectores terrestres de tercera generación y en el Observatorio Espacial LISA, en este último caso a través del grupo del Instituto de Ciencias Espacials de Cataluña, liderado por el doctor Carlos Opuerta. Finalmente, me gustaría también señalar la participación de muchos grupos españoles en el seguimiento de las contrapartidas electromagnéticas de las fuentes de ondas gravitacionales. La lista en particular incluye Integral en el Centro de Astrobiología CSIC-INTA y la Universidad de Valencia, la Red BUTS y VLT en el Instituto de Astrofísica de Andalucía, Master Chandra y Gemini en el Instituto de Astrofísica de Canarias, DES Spain en el Instituto de Estudios Espacials de Cataluña, la Universidad Autónoma de Madrid y el CIEMAT, Fermilat en el IEC y ICREA, Agil en la Universidad Autónoma de Barcelona, Vinrush en el IAA, EPESTO en el IEC, Toros en el Centro de Estudios de Física del Cosmos de Aragón, HOC en el IAC y Euro VLBI en el IAA, y también en la búsqueda de neutrinos de alta energía, en particular Pierre Auger en el Instituto Galego de Física de Altas Energías y Antares en el Instituto de Física Corpuscular de la Universidad de Valencia, CSIC. Y con esto pues, me gustaría ya dar la palabra al profesor Barish para que nos cuente la detección de ondas gravitatorias.
Hi. I'm always comfortable in a physics lab, and therefore, being in a fantastic science museum like this, I am immediately comfortable compared to some auditorium somewhere. So anyway, what I'm going to do today is to try to have you understand the background, not all the details of what we've discovered or will discover, but what it took to both understand theoretically what had to be done and experimentally in order to detect gravitational waves. The picture on the left is essentially what we saw on September 14th, two years ago, 2015, 3 years ago. And that picture basically comes straight out of the apparatus. Hasn't gone through a tremendous amount of data analysis or anything complicated. My goal this evening is pretty simple. It's that everybody that's here and spends an hour listening to me understand this picture well enough to be able to explain it to your kids, your wife, your husband, because if you understand this picture, you pretty much know what makes gravitational waves. Interestingly, this picture right here now appears on a tie that I wore in Stockholm, on dresses and so forth, because some designer has grabbed it and thought it was artistic. Of course, it's scientific, not artistic. What's shown is 3 panes. The top one is the data from one of the 2 LIGO detectors in Hanford, Washington. I'll describe all this in detail, but I'll just give you some words. The second one down looks identical except a different color. And it is data taken 3,000 kilometers away in Livingston, Louisiana. The bottom is no more than putting one on top of the other, which should impress you that they look so much alike each other. And drawn through this is a little thin white line that you probably can't see. The reason you can't see it is it follows the curves so well. And it's the predictions of Albert Einstein for 2 black holes colliding, which is what we interpret this event to be. The scale on the bottom is the scale of seeing the last 0.2 of a second of this in-spiral and collision of 2 black holes. So time is going across. And the scale, and the most important one, is the vertical scale. It says strain. Strain is a concept from general relativity, and it translates to us being able to measure a small effect, which I'll describe to you. What's important is the size of it. It says 10 to the minus 21, if you can read it. And I'll try to describe to you what that means in terms of trying to make a measurement, a discovery, and how we succeeded in doing that. So that's the goal. If you understand that picture, I'm a success. What we saw, and I'm going to tell this story pretty much historically, began 1.3 billion years ago in the distant universe. 1.3 billion years ago is when on Earth we were just evolving from single cell to multi-cell life. So that's how long ago this story starts. At that time, these 2 black holes were in orbit around each other, like the Earth is around the sun. So they're in orbit around each other. As I'll describe, by Einstein's theory of general relativity, they lose energy as they go around each other and eventually spiral in and crash into each other. It's the last part of that that we observe. This picture is drawn from a computer emulation of the data that we detected. So it's not an artist's conception or movie, but that. I'll show you them going around each other and merging in just a minute. But first, let's make sure that we all have some picture of what they are. A black hole. We all know kind of from the newspapers and everything what a black hole is. It's a mathematical concept, but it's also a physical concept and a real one. Basically, a black hole is a region of space where the gravitational field is so strong that nothing can escape, not even light. So that's maybe a physical concept, but it can happen and does happen from physical phenomena. So they form, we think, mostly, and the ones that we observed, from the merger, from the dying of a large star. A star, as we all know, burns, keeps us warm and light by a fusion process. Same fusion process that we know. The fusion process burns up first the light elements, hydrogen, helium, works its way up to heavier elements. Eventually, as it burns up the lighter elements, it gets up to iron. By the time it gets to iron, it can't burn much more. And at that point, we don't have the outward force of fusion counteracting the inward force of gravity, and a star, when it dies, collapses. When our sun collapses, it'll make some sort of massive object that's very compact. If the star is big enough, much bigger than our sun, maybe 3 times the size, when it collapses, it actually can make a field strong enough to be like what I said here. Nothing can escape, and it's a black hole. We think that's possible for stars that die of masses of about 3 times the mass of our sun, up to maybe 100 times the mass of our sun. It's also possible that these kind of black holes were formed in the Big Bang itself, or primordially. We don't really know whether the ones we have found come by the collapse of a star that I said, or maybe primordially, or maybe some other way. That's the research for the future. What we do know is that they're black holes. They obey these conditions. They don't give, they've been looked at very carefully, electromagnetic radiation, which other phenomenon that give gravitational waves will, and I'll talk about one at the end of the talk. So finally, let me mention that you hear and read in the newspapers about supermassive black holes. Those are prevalent in our universe at the centers of galaxies, and they're really a different phenomenon, except for the fact that they're also black holes. They have the first feature that I said. So that's a black hole. The distance and size that I'm talking about physically for these black holes, by the time we see them, they start far apart. But as they lose energy and merge into each other, by the time we see them, shown on a map of Spain, there are 2 black holes that are about as far apart as Valencia is from Madrid. So believe it or not, we're talking about 2 black holes that aren't very far apart. Each of them is about the size of metropolitan Madrid, but they have a mass that's in one case 29, the other case 36. We know that from our fitting of the data, times the mass of our sun. To put that in perspective, that's 10 million times the mass of the Earth. So these are just this far apart. Each of those black spots are about 10 million times the mass of our Earth, so they're very massive. And as I note, they're going around each other at about half the speed of light. So that's basically what's happening. And this is taking the data that we have and showing it in a computer screen, the last instance of this merger. As they go around each other, they're losing energy to gravitational waves. They get closer and closer together. They affect everything around them, of course. And then they finally merge. This is the very strong field gravity that was talked about in the introduction. And then there's some shaking at the very end as it all settles down. And then you end up with one black hole that's much bigger, in our case, about 60 solar masses. That's the phenomenon that we witnessed, and we witnessed others since then. As they merge together, they emit gravitational radiation. I'll talk about the details of what gravitational radiation is. That started 1.3 billion years ago, passes through the universe, eventually comes to the Earth, and by the concept that Einstein gave us, they distort space and time. So they distort the Earth somewhat as they go by. And this picture is exaggerated a little bit. In fact, a lot. So we can't really measure the distortion of the Earth itself, and instead we build an instrument that's sensitive enough to do that, and that's what I'll describe. So that's the background, and that's the goal, to be able to describe all that. As it came to the Earth, we then had a detector that was able, that I'll describe, that was able to detect it. And we saw coming up from the southern hemisphere first, in this region, it hit the Earth. That position that it came up in the southern hemisphere was determined by more or less triangulation, like you're used to when you have different sources and want to know where you are. In this case, the 2 detectors, LIGO detectors, the difference in when the signal arrived in one, when it arrived in the second one, and a comparison of the amplitudes of the 2 give us this information. As was mentioned in the introduction, the addition of the third detector, which we now have, but I won't be able to talk about in this general talk, has narrowed this by so much that we're now able to compare whether telescopes see the same thing we do, and I'll show a little bit of that at the end of the talk. So this came up in the Southern Hemisphere on September 14th, 2015, about 4:50 in the morning, a.m. in the morning, in Louisiana time, because they hit Louisiana and made this signal in our detector 20 milliseconds later. And this signal's the one we're going to describe, and that's basically the data. Seven milliseconds after that, note 7 milliseconds, we get the second signal halfway across the US, 300 kilometers apart, and to your eye, they should look almost the same. And then I've drawn the line through again for you from Einstein's fit, using the parameters that I described, the mass of the two black holes and the merger. And these we calculate from Einstein's equations. Okay, so now let me talk about the science a little bit, how we've developed the concept of gravitational waves themselves, and starting from something that we all learned in school. So I'll start from Newton, again historically. So Newton in 1687 wrote an important book called the Principia. That book, in it, has the description of the scientific method, which we all use. But it also has his universal gravity. And Einstein basically called it universal because the formula that he used, which is given here, worked for everything. It worked for the apple falling out of the tree, worked for describing the moon going around the earth around the sun. Later, when we cared about it, the tides, the escape velocity to get off the earth for a rocket, and so forth. It describes essentially everything to do with gravity. It is a formula we learned in school, which is it's the product of two masses and divided by the square of how far apart they are, times some constant that's how strong the strength is. That took another 100 years to measure. And that gives you the force of these two objects. He did the calculus in the Principia and showed that you could take the center of gravity of each of these objects. So that was the theory of gravity, the most successful physics theory, arguably, of all time. Described everything that involved gravity that we cared about from 1687 basically until Einstein's time. So what happened next, and why does Einstein come along, and why do we have a new theory of gravity if this is so successful? This has a couple conceptual issues, which I'll come to, which is probably the motivation for what Einstein did. But before that, let me talk about a little bit about celestial mechanics. This man, Urbain Le Verrier, a Frenchman, was called the father of celestial mechanics. He got tagged as the father of celestial mechanics because he made a big discovery in a rather dramatic way. He basically used Newton's theory of gravity and Kepler's laws to see if all the planets obeyed them very well. And he noticed that the orbit of Uranus didn't quite fit the calculations using Kepler and Newton's law. He then hypothesized that that was because he was neglecting another planet. And he did the calculations to determine what would be neglected to make the calculations correct. And he found that there would be a planet that would be missing. He gave it a name, Neptune. He sent a letter he didn't do what we do now, which is send a letter to be reviewed and blah, blah, blah. He was more dramatic. He sent a letter from Paris to Berlin, to an astronomer in Berlin. He gave 5 days for the letter to get from Paris to Berlin at that time, told the astronomer where to look up in the sky, And then within 1 degree, he found Neptune, and that was the discovery of the planet Neptune. And this made Urbain Le Verrier a very famous scientist in the 19th century. This was done in about the 1830s. He then noticed a second problem, and this gets closer to what we're going to talk about in gravitational waves, and that is that in the 1850s, he discovered that there was also a smaller effect, but an effect for our smallest and closest planet to the sun, Mercury. So Mercury goes around the sun in a very elliptical orbit. And as it goes around the sun in an elliptical orbit, because of the positions of all the planets, it comes back to a slightly different place, and you can calculate how far it'll move in this daisy-like pattern. And when you calculate it, when he calculated it, the answer using Newton's theory is about 10% wrong. It's 532 arcseconds per century versus the actual measurement, which is about 10% larger than that, 575 arcseconds per century. Clearly, because he had become famous by saying then something's missing, he proposed that there's another planet or matter between Mercury and the sun. That was looked for, and in the 1850s and the 1860s, there were false discoveries, people who claimed they discovered something between Mercury and the sun, but none of that stood up to scientific scrutiny. So by the time Einstein came along, which is the early 1900s, this puzzle still existed, but was probably not much of the motivation for Einstein developing a new theory of gravity. In fact, this problem still could have been due to matter between the Mercury and the sun, and in fact there was a rather ambitious NASA mission well after Einstein's time to look for matter between Mercury and the sun. They didn't find any. And so that problem went along. Einstein entered this problem in a different way, I think. In 1905, Einstein solved several of the most important problems in physics that hadn't been solved in a matter of months. More or less once a month, he did something that was new. And for physicists, he was a great hero from 1905, and in 2005, we celebrated the 100th anniversary of Einstein's incredible year. During that time, one of the discoveries that he made, or one of the theories that he put forward, was what we call special relativity, E equals mc squared. And that basically is a theory of what happens when we have high velocities near the speed of light, and the theory that nothing can go beyond the speed of light, and masses get heavier, and so forth and so on. So that's the theory of special relativity. The theory of general relativity, which instead of taking 1 month for him to develop, took another 10 years for him to develop, he produced in 1915. So he had the motivation to work on that for a very long time. He did a few things in between, but not very much. So he worked on that for 10 years. What it amounted to was basically adding to the theory of special relativity accelerations, not just velocities, but accelerations. Accelerations basically mean gravity, and so that's the theory of gravity. So he came up with a new theory of gravity. That theory, when he put it forward, immediately gave the right answer for this, but this wasn't a very big problem. That doesn't make you overthrow 200 and some years of Newton's theory. His theory of gravity was rather complicated. I'm not going to explain this formula, but I use it just to use one formula like I did for Newton. And his theory basically has the feature that it combines space and time. So we all know that space is three-dimensional, X, Y, Z. And in Einstein's theory, he adds time. And it's all unified together, and it's one word, space-time. Bill Gates doesn't understand that yet, so when you put it in Microsoft Word, there's a little wavy line underneath. But everything that we do unifies space and time into one four-dimensional concept. That's very difficult to see, and it's very difficult to explain, and it's very difficult to calculate. Einstein, when he put this together, and I'll talk about it a little bit more, but when he put together this idea of putting space and time together, and adding acceleration to special relativity, he solved, if this is the right theory, the two basic physical problems with Newton's theory. The first problem with Newton's theory, and Newton realized this one, is that it has what we call in words instantaneous action at a distance. That is, when something happens, the apple falls, you see it right away. That's okay for the apple. But when something happens in the distant universe, or the sun, if the sun were to burn out, it takes 7 seconds for the light to get to us. We wouldn't know until 7 seconds after the sun burned out. But a gravitational signal, if it was Newton's theory, would be detectable immediately. And that doesn't make very much sense. In Einstein's theory, the speed that he used, the velocity of light, in the special theory of relativity is as fast as information can travel, and it's the same speed that exists for what will become gravitational waves. So the speed, finite velocity of travel of information is fundamental to Einstein's theory and solves the conceptual problem that Newton had. The other problem is one that is almost embarrassing for most of us, because we went to school as school kids and we were told that when the apple falls, the earth pulls it down. When we jump up, the earth pulls us down. And we may have learned the little formula that I showed, but I don't know how many of you, but I didn't ask my teacher this fundamental question of how the earth pulls us down. Basically, that's missing from Newton's theory. He gives you a theory or a formula, but you have no idea why the earth should pull the apple down, or why these two masses attract each other, and so forth. And in fact, for 100 years or so, people tried to explain how it happens, usually with electromagnetic arguments, which are wrong. So that was just missing from Newton's theory. Einstein, on the other hand, developed the idea that space and time are in one, and when you put a massive object into space, it distorts the space and time around it. So that's shown in this grid on the left, where I have the sun and I have the earth. And you see the distortion of the grid caused by the presence of the sun, another little dimple caused by the presence of the earth. And if you look at any place on there, I can only show it spatially, but there's also a distortion of time everywhere as well. So it's this distortion of space and time. Looking at that picture, you can get an idea then that the earth wants to roll in toward the sun, or if that was a ball, it's the fact that it's going at a velocity around it, that by what we call centripetal force, that it's kept in an orbit around the sun. If you then think about what I just said, it didn't matter whether the earth had any mass. Einstein realized that, so he projected the fact that light, as well as a massive object, would be distorted by the presence of another massive object. Basically would be attracted in the same way, because the sun, for example, just distorted the space around it. And he invented an experiment. He did this in 1915. The idea was the following, shown on the right-hand side, and that is, if I have some stars that start moving behind the sun, and I watch them, as they get near the sun, the trajectory that comes to us will get bent by the distortion of space and time around the sun itself. And clearly, you can't look at the sun and see that. so he developed the idea that it should be done when there's a full eclipse of the sun. And that experiment was actually done successfully in 1919 by Arthur Eddington, who as a result became Sir Arthur Eddington. And that basically showed the bending of light in a full eclipse as light went around the sun. This, by the way, is what made Einstein a household name. It wasn't solving special relativity in 1905 or whatever else we idolize as physicists, but the bending of light. The bending of light became something that hit every newspaper in the world and made Einstein a kind of famous person. So by 1919 or 20, he was worldwide famous. All this is background for the fact that in 1916, only 1 year after he had developed the theory of general relativity, he predicted gravitational waves. Before I do that, which I'll do next, let me do one final thing with general relativity. General relativity, everything I said in words, still undoubtedly feels very abstract to all of you. But you use it almost every day, probably, most of you. And that is GPS. GPS, I'll remind you, works by a bunch of satellites. There's 24 of them that circle the Earth. At any given point when you're standing somewhere, a few of those satellites, maybe 6 or 4 or 3, depending on where you are visible. And the time it takes for a signal to go back and forth is used to determine where you are, and that's how the position is located. But did you realize that inside the satellite, we have to make some corrections or we get the wrong answer? The first one is Einstein's 1905 theory, the theory of special relativity. That theory says, we learn it when we are students of physics, that if something's going very fast, the clock that you're holding will tick more slowly. It's Einstein's words. Moving clocks tick more slowly. That happens, and we don't notice it, of course, at the velocities we have on the Earth, but satellites are going at 14,000 kilometers an hour, and that's fast enough that you need to make a correction for this relativistic effect, and the clock's going more slowly, and it's about 7 microseconds a day. That correction is made in the satellites themselves. A second correction is made in the satellites, and that's my subject, general relativity. And that is because the satellites are high enough above our surface of the Earth that the gravitational field is only 1/4 of what it is on the Earth's surface. When that's true, it turns out that clocks tick faster because they have less gravity. And that correction has to also be made, and it's 45 microseconds per day. So the total correction made in the satellites in the GPS system is 38 microseconds per day. I don't have time to go through the numbers for you, but if I translate that to the accuracy we have on the Earth's surface, and I did not make that correction, I assume a road is 10 meters wide, how long would it take before I wouldn't be able to stay on the road? It's about 2 minutes. So the correction is absolutely essential for GPS to work, even at the accuracies that we need just to drive a car down the road or find our friend's house. Okay, on to general relativity, the effect of gravitational waves. So in 1915, he developed the theory of general relativity, and in 1916, in looking at the equations of general relativity, he noticed that if he formulated general relativity in a particular way, that the formulas, different letters of course, but the formulas had similarities to the formulas of electricity and magnetism. Electricity and magnetism have waves. We have electromagnetic waves, radio waves, light waves, infrared, ultraviolet, microwaves, and so forth. So he projected from just the similarity of the formulation of the equations that there must be also connected to this new theory of gravity, gravitational waves. He did not develop it from the inside of general relativity or from first principles, but he did it by just this analogy. Another thing that Einstein was very good at. I mean, he developed these fundamental theories, but he also had an intuitive way to make the physics interpretations. So he published a paper in 1916, and that paper, except for the fact that it predicted gravitational waves exist, is a terrible paper. It basically doesn't develop anything from first principles. He conjectures that there's gravitational waves, and he even makes a mathematical mistake of a factor of 2, which would have been awful for us in predicting our results if that wasn't fixed. He wrote a second paper in 1918. And in 1918, the second paper was somewhat better. He still didn't develop gravitational waves from the heart of general relativity, but he clarified basically what's happening. And most importantly, he gave us the information to detect gravitational waves or to make a source of gravitational waves, what makes the source of gravitational waves. And he has in it the fact that how gravitational waves can be made. To remind you, electromagnetic waves are made by taking two charges and oscillating them a little bit at whatever frequency you want the electromagnetic wave to be. So 10 times a second, 100 times a second. And a physicist named Hertz in the 1880s made a source like this, went in the next room, and detected the waves that came, electromagnetic waves. And then he moved his detectors forward and backward and showed that they look like waves. So you would like to think that maybe you could do the same thing as experimentalists for gravitational waves. I'll come to that. Einstein left the problem after 1918, and nobody else really picked up on it. In fact, general relativity itself was not a popular subject for physicists. Quantum mechanics was beginning. Quantum physics was what most people were concentrating on. Einstein himself was concentrating on trying to unify electromagnetism and gravity, which he didn't succeed in doing. But he returned to this problem in 1936. In 1932, he came from Berlin to the US, and he was at Princeton University. He wrote several absolutely important papers, but at a speed of 1 a year at that point. And by 1936, he wrote this paper. The paper was his attempt to actually develop general relativity from the first principles. He entitled the paper, his co-author was Nathan Rosen. He entitled the paper, "Do Gravitational Waves Exist?" It should be obvious to you that if he's said gravitational waves exist 20 years before, why is he questioning it now, 20 years later, when he hasn't talked about it before? And the problem is he developed doubts. And that has to do with, again, the difficulty of the fact that we have this theory now that mixes space and time four-dimensionally, and making the calculations is very difficult. And if you don't formulate it very, very carefully, you often get what we call coordinate singularities, or singularities or infinities in the formulation. And that's what he did. He developed it, he found these singularities, he got worried that what he then thought were gravitational waves was an artifact and wasn't real. And he didn't declare that it was unreal, but he expressed his doubts in a paper that he wrote and submitted to Physical Review in 1936. The editor of Physical Review at that time was named John Tate. He was a young man. And this is just the time, in physics at least, in the US, I don't know about Germany, where Einstein came from, that peer review that we all use so heavily in determining whether something's worth publishing or not, was just being instituted. Peer review means that you submit your paper to a journal, it's sent out to anonymous reviewers that are experts in the field, and you get their comments whether it's worth publishing, right or wrong, and so forth. In this case, in 1936, the editor, John Tate, had the freedom to just accept an article if it came, or reject it out of hand, or send it out for review. This article he sent out for review, and he sent it to a man who we now know who he is, even though it was anonymous at the time, Howard Percy Robertson, who was also an expert in general relativity and happened to be on sabbatical at my institution at Caltech at that time, and he got the article to review. He saw the mistakes in the article where they had these coordinate singularities. He reformulated it in what we call cylindrical coordinates. He sent back his review to John Tate. John Tate sent, I don't have time to show these, but I have it, a very modest letter to Einstein saying, what do you think about these comments? Somebody else that had submitted an article, they would have just rejected, of course. And Einstein wrote an angry letter back to Physical Review Letters saying that he didn't ask to have his article reviewed. He asked them to publish it. He withdrew the article, and he never again published in Physical Review. So Einstein basically did publish the article. He corrected the mistakes because Howard Percy Robertson went back to Princeton, talked to Rosen, and the corrections were made, and it got published. I illustrate all that to say partially that whether gravitational waves exist was still rather doubtful and unclear even to the biggest proponents as late as, say, 1936. Einstein never wrote about it again. By the 1950s, it still was doubtful, and most people in this field attribute, if you had to pick one place, a meeting in 1957 in Chapel Hill, North Carolina, to the time when theorists in the field finally agreed that gravitational waves exist. That meeting was attended by about 40 experts in general relativity. So these are the experts in general relativity. The first talk in that meeting was given by a man named Pirani, and he made a very elegant derivation of gravitational waves from general relativity. That's formally one thing you need. A second feature of that meeting is that Richard Feynman was at that meeting. There's a story, true or not, I don't know, that he registered as Mr. Smith because he wasn't regarded as a general relativist expert. But he brought up another point, and that is that if, which is more physical, if gravitational waves exist, they have to be able to transfer energy. So he made an imaginary or Gedanken experiment, which he called the sticky bead experiment, to make a concept for how gravitational waves could transfer energy. And it's shown in the right side. So imagine two beads on a bar, and then gravitational waves come through. Remember, what gravitational waves do is distort space around them. And so it distorts the bar at the frequency of the gravitational wave. That moves these and puts friction on these little rings. Friction is heat, heat is energy, and so basically you can transfer energy if a gravitational wave were to go through something like this. So at this point, if you have to pick a time, the idea of gravitational waves, which was put forward in 1915, it was 42 years later before it was taken seriously that they actually exist by the theoretical community. I say that as an experimentalist, so the whole 100 years it took us to see if this is right doesn't get blamed on us. It took theorists 40 years. So anyway, Einstein's theory of gravity then, to make gravitational waves, has a form to make a quadrupole moment that looks a little bit like the picture here. And you can imagine this picture being two black holes going around each other like we saw, and the gravitational waves emerging from that at the speed of light. So it took 1.3 billion years to get to us. Okay, so now we're going to attack the problem experimentally. And attacking it experimentally, the first thing and most important thing usually that you'll learn as an experimental physicist is to make sure, if you want to get the right answer, that you control everything. That Hertz did that. He made a source to make electromagnetic waves. He made a detector to detect them. He moved the detector. There was nothing that wasn't out of his control and something he could check. So ideally, you'd like to do the same thing for gravitational waves. Make a source. So I'll try to make a source like we could make. Imagine a barbell like this. And imagine that on each end of the barbell, I have 1,000 kilogram weight, pretty heavy. The barbell's maybe 1 meter long, and I spin it at 1,000 times a second. I better get out of the lab to do that. And when I do that, then I have to try to detect it, and I go 300 meters away, just for the purpose of calculating how big the effect is. That's not far enough to see the wave-like nature of gravitational waves. You'd have to be much further. The effect would be smaller. But I've exaggerated the numbers as large as I possibly can, and I get a number of 10 to the minus 35. Remember on the first slide, and what I'll show you as I show you data, is that we are now detecting effects as large as 10 to the minus 21. The symbol on the left, the little h, is called the strain. It's the size of the distortion of space-time in Einstein's theory. So even though it would be nice to control everything, we can't do it. We can barely measure something 14 orders of magnitude bigger than the effect we'd have if we invented our own experiment. So instead, we have to rely on nature. And luckily, nature turned out to be pretty interesting for us. So we have the question of 2 black holes. I do the same calculation. And if I put the numbers in, they're each, as I said in the very first slide, about 30 times the mass of our sun. They're about 100 kilometers apart. They're going around each other about 100 times a second. And the distance away, I wrote it here in astronomical units, megaparsecs, is about 1.3 billion light years. If I put those numbers into the same formulas, ignore the formula, I get that 10 to the minus 21. So 10 to the minus 21 is what we have to measure. It's the size of the distortion of space-time. In Einstein's equations, it's a little h called the strain. For us as in doing an experimental measurement, it represents the change of length over length physically that is distorted by the passage of gravitational waves. So that's what we have to measure. And now I'll talk a little bit and give you some idea what it takes to do that. First, the picture of what I was showing is shown here in an old cartoon that we drew years ago. What I showed was the very left-hand side of this part here, which is the 8 or so wiggles that got bigger as we entered. Then they merged together. This merger part is where the fields of gravitational waves are the strongest. It's where, as we get into this subject more, we'll be able to test very rigorously general relativity, and at the end, it has to settle down, what we call a ring down. I show on the right only to show you that, because I'm going to show you some data in a few minutes, that depending on the mass of the objects, the frequency that they'll get to is less if they're more massive and higher if they're less massive, as shown in these pictures, and I'll show you that in some data in a few minutes. Okay, so let's see what gravitational waves do when they go through some detector that we're going to build. The amplitude that we're going to look for is 10 to the minus 21. That corresponds to a change of length of 10 to the minus 21. So now imagine that you have a circle with masses around the circle, and they're free to move. They're not rigid, but they're free to move. If we then put a gravitational wave into the board, into this slide, what it does is distort the circle, make it more elliptical, first in the direction that I showed, a distance that's the 10 to the minus 21. And then, depending on the frequency of the gravitational wave, it'll go the other way. First tall and thin, then short and fat, tall and thin, short and fat. That's the phenomenon, and the size of it is 10 to the minus 21 meters. Let me remind you what 10 to the minus 21 meters is. We decide 10 to the minus 21 is too small to measure. So instead, we use brute force and make detectors that are a kilometer long. So then delta L over L is not over 1 meter, but over a kilometer. So the size that we have to measure is 10 to the minus 18 meters if we make a very big detector. So how small is 10 to the minus 18 meters? We all know what a meter stick looks like. It's so big. A human hair is 100 microns. That's 10,000 times smaller than a meter stick. And we all know what that is. I don't have very much anymore. Then the wavelength of light, like the light in this laser beam on here, is about a micron. And that's 100 times smaller than the human hair. The atomic diameter, which you can see demonstrations around this museum, is 10 to the minus 10 meters, or 10,000 times smaller than the wavelength of this laser light that I'm holding in my hand. So that's pretty small. That's an atom. If I go to a proton, which is what we use in big particle accelerators or what we're made of, that's 10 to the minus 15 meters, or 100,000 times smaller than an atomic diameter, and we claim we've measured something that's 1,000 times smaller than the size of a proton. So that's why I have to talk about the experiment a little bit. It's challenging. Okay, so what does it take to do that? It takes a lot of things, and I could talk for hours, of course, but there's basically two main challenges, and I've boiled it down to those two challenges. That is, I have to measure this 10 to the minus 21. I make a detector, ours in LIGO are 4 kilometers long. Then what do I have to do? I have to do two things. One is I have to do interferometry, which is what we're measuring, which I'm showing here, and I'll show you a little bit more about interferometry. We have to do interferometry using light beam to measure change of length to 1 part in 10 to the 12th of the wavelength of the light itself. Generally, if you've ever been in a freshman or sophomore physics lab, they often have an interferometer as an experiment that you look at, and you see these little fringes. The fringes are basically, each one is a wavelength apart, and you can measure maybe 1/10 of a wavelength, or maybe if you think you're good, 100th of a wavelength. But 1 in 10 to the 12th takes a lot of work. Most of the innovation in LIGO is optical, and it's creating enough light, enough tricks to be able to do the interferometry well enough to measure it to 1 part in 10 to the 12th. We had solved that problem maybe 10 years ago or 8 years ago. So we had learned how to do this part of the problem that long ago. We're even doing better as we move in the future. The second part of the problem is what I want to concentrate on, because it's what had to be developed to make for us to make the discovery. We put this experiment here on Earth. I showed you a picture of it. And unfortunately, the big problem that we have to deal with is the vibrations of the Earth itself. The Earth is terribly vibrating. It's not stable. And we have to reduce the vibrations of the Earth in the region where we made these detections by another factor of 10 to the 12th. And that is the big problem that we dealt with for so long. In our case, we had reduced this to but 1 part in 10 to the 10th by the time that, I'll play this movie while I'm talking. 1 part in 10 to the 10th, this shows an interferometer working, and when the arms get different, you get a signal in the light. But we have to stabilize this to 1 part in 10 to the 10th. I'll tell you in words how we do that. First, the scheme that we use is the same scheme that you use in your car to avoid bumps. So when we drive our car down the road, in addition to having GPS to see where we're going, it's very smooth when we go over and hit a bump. That's done with a shock absorber. That shock absorber takes a high-frequency bump and smooths it out. It can't get rid of the energy. It smooths it out. It makes it much lower frequency, and you feel just a little gentle motion as you drive smoothly down the road in your car. Those shock absorbers are made out of a material that absorbs and re-emits the bump at lower frequencies. Basically, LIGO, as it was made, the scheme is a little different in Virgo. I'm not going to differentiate, but I'll just talk about LIGO. The scheme that we've had was to make the fanciest, simple shock absorbers that we knew how to make. Like you have in your car, they're springs with just the right gushiness. And we were able to do that in 4 different stages to try to eliminate as much as we could the shaking of the Earth. The amount that it succeeded in doing is reducing the shaking of the Earth by a factor of 10 to the 10th, as I said. So we basically then had to get another factor of 100. I'll tell you how we did that, which is the key to making the discovery, in just a minute. First, we built 2 4-kilometer LIGOs, one in Livingston, Louisiana, which I mentioned before, one in Hanford, Washington. You might notice that Caltech and MIT, the 2 collaborating institutions that started this, aren't at the 2 stations. We submitted a proposal to build one in California, one in southern Maine. They approved building LIGO, but they moved it like this. And as a result, we had 2 very supportive senators for the years that followed. They're 3,000 kilometers apart. It takes light 10 milliseconds to go from one to the other, which means if a signal's coming in from below and went to Livingston first, it would happen as much as 10 milliseconds before Hanford, and going the other direction, 10 milliseconds at Hanford before. A gravitational wave signal, which goes at the speed of light, has to be within that plus or minus 10 milliseconds, which is what we use as a constraint on making sure that we see a signal together. You'll recall the first signal was 7 milliseconds apart. This is a picture of the 2. The instruments are absolutely identical. Every time we change something in one, we change it in the other. But physically, the environment is totally different. This is high desert in Hanford, Washington, and swampy pine forest in Livingston, Louisiana. This is just to show you what the insides look like. These are the big tanks. A man is about a third as tall as this. These are the big tanks that house the mirrors, the lasers, the baffles, everything that we do inside. And out the ends off the picture are the 4-kilometer long beam pipes. Those beam pipes are evacuated to a very high vacuum. So let me give you a hint at all the things we had to develop, but concentrate on one, which is how we get the last factor of 100. First, we have to use vacuum. In 4 kilometers, if the particles scatter off molecules, they find a path that takes them longer to get all the way down and back, and that would give us false signals. So we work at high vacuum, and LIGO has the largest high vacuum system in the world, 16 kilometers of 10 to the minus 9 torr vacuum. The largest vacuum system in the world is at CERN on the Large Hadron Collider, but it's not all high vacuum. Ours has to be high vacuum. The second is that we need an incredibly precise laser. So we've developed a laser which has a single line that transmits light in the ultraviolet at the wavelength that we reflect off the mirrors at the ends, and it's stabilized for its amplitude, pointing, and so forth. That's that. The third one, which is what I'll come back to in a second, is seismic, isolating ourselves from the ground. And that, as I said, a factor of 10 to the 10th of that, we've gotten by passive isolation. There's other problems. We work at room temperature. At room temperature, molecules move around inside our mirrors, and that limits us some. And we also have the problem that we try to have as many photons as possible to make the measurements accurate, and that creates the problem that if you have too many photons, it puts pressure on the mirrors. So all these problems I'm not going to talk about, but let me talk about the seismic noise one as I show our sensitivity. So this is schematically how sensitive a gravitational wave detector like this works. The frequency band, you'll notice on the bottom, is basically the audio band, 10 hertz to thousands of hertz, just like our ears. That's not an accident. Our ears have evolved through time to basically work where the Earth is quiet enough so we can communicate with each other. Below 10 hertz, at low frequencies, the Earth makes so much vibrations that we wouldn't want to communicate there. At the highest frequencies, the ears cut off because you can't sample fast enough at high frequencies, so you can't hear what comes in when you have to go to sample so quickly. It's the same thing for us at high frequencies. We cut off because we basically don't have enough photons. We have nothing to do with audio, like audio signals, but the shaking of the Earth gives us the same problem, that the quietest place to do LIGO is in the audio band. So that's what we do on the Earth's surface. The shaded region, when I take all those backgrounds that I talked about, is the region where we're sensitive to gravitational waves. So you'll notice it goes from tens of hertz to thousands of hertz. As this black hole collision came in, the first part of the signal that we saw was more like 10 hertz or 20 or 30 hertz, and it moved up to 100 or so. And I'll show you some other signals that moved to even higher frequency. This is as good as we were when we had 10 to the 10th isolation, seismic isolation, and had run LIGO for a decade after building it and never saw gravitational waves of any kind. The two different colors are just two different configurations where one of them we changed the optics to emphasize low frequency and one of them high frequency. The little dark line that goes through is basically our calculation of if the apparatus worked exactly as we designed it, what it would give. So we were essentially there except at the very lowest frequencies. We then made a plan. This is, we started on this 15 years ago, but we made a plan to improve the sensitivity at least a factor of 10 everywhere. Now, what does a factor of 10 do for you? A factor of 10 directly tells us we can look 10 times further out in the universe. If we can look 10 times further out in the universe is actually that we're looking at is 10 cubed by the volume times bigger than it was originally. So we see 1,000 times more. So the improvement of a factor of 10 would give us 1,000 times more rate or sensitivity. So that was our goal, and we started building the improvement about 2010 or 2011. In the medium frequencies, we improved things, and I'm not going to go through the details, by making better mirrors, test masses, ways of suspending them, and so forth. And at low frequencies, we had to put in better seismic isolation. And as I said, this ends up being the key to the measurement that we made. So what did we accomplish? We turned back on, we built a new apparatus. I'll tell you what we did. With a higher power laser, with better mirrors, and with better seismic isolation. And we moved from the upper curve to the middle one, where you see two colors in the middle one. The two colors are one from our detector in Hanford, Washington, one from the detector in Livingston, Louisiana, and they look alike. The bottom line shows you that we're going to get better in the future. Our design is to get to the bottom. But before that, we decided to take data and run because we had improved a factor, at least a factor of 3, which gave us a factor of 27 improvement, the cube of 3. That meant in a short amount of running, we could do better than we had done in 10 years previously. So we decided to run. At low frequency, though, we actually had improved a factor of 100. That factor of 100 brought us from 10 to the 10th to 10 to the 12th isolation. How did we do that? We did that by not inventing some magic, but by actually doing something else that's done in nature, done physically in places, but maybe better, like we did the shock absorbers better. We did what we call active seismic isolation. The idea is simple. You know, if you take an airplane, many of you have taken an airplane and buy these earphones that you put on, those earphones make it quiet and you don't hear the roar of the engine. What are they doing? They're measuring the ambient noise from the engine and canceling it. And since the engines kind of make the same noise, it cancels it. When the stewardess talks to you, that's not ambient. You still hear the stewardess talk to you. So these are almost like magic. It gets rid of the ambient noise and not the other noise. In our case, we don't have noise. It's not audio, but there's still residual shaking of the Earth. We instrumented LIGO with seismometers that told us what the residual shaking of the Earth was, what its direction is, and then made active compensation for it. We basically pushed the other direction on the test masses so they didn't move. And that gave us the factor of 100, adding the active seismic isolation. So that's what we got there. And then the next thing you knew, we started detecting gravitational waves. What you see on the top is the one I showed on the very first slide. It's the biggest because it's black holes that were big and heavy, and that it wasn't terribly far away, even though 1.3 billion light years sounds far. The middle one that goes out 15, 12, 26 is an example. It was the second one we detected, actually, was much lighter. So, and as I said, if they're lighter, they go to higher frequency, and it has many, many more oscillations. Even though it's smaller than the top one, when we try to test the details of general relativity, how well general relativity fits the data, the fact that this has so many oscillations actually gives better fitting. We basically use the combination to do the best we can. So these are all black holes, and we've detected a bunch of those, and now are interpreting those. First thing, and I show a kind of old slide here, but is to ask whether gravitational waves that we've detected are like Einstein's gravitational waves, or maybe have some quantum effect that is coupled to them, like electromagnetic waves, which have photons. So a way to test that, at least one possibility, is that there's some object, we call it a graviton, connected to the gravitational waves, and it has a tiny amount of mass. We don't see any, so then we look for distortions in those wiggles. We don't see any. Within the limit of how well we can measure the wiggles, we can put a limit on how massive this graviton can be, and the number is incredibly small. We're even better now when we've added more data, but it's 10 to the minus 22 electron volts over the speed of light squared. Okay, so in time, we're going to study general relativity much better, and hopefully determine whether Einstein's formulation of general relativity or alternate ones are right, and how right in this very strong field limit. The second part of what we're doing, other than having seen gravitational waves, is to begin to do gravitational wave astronomy. That has initiated, we've always thought that gravitational wave astronomy, once you can do it, is going to see a very different sky than electromagnetic waves. Everything we know in astronomy has come from electromagnetic waves. Some phenomena we see in different wavelengths, different in radio, infrared, ultraviolet. But basically, they all have to have some phenomenon that gives electromagnetic waves. Gravity is a different phenomenon in the universe. So we expect that as we look at the universe with gravitational waves, we'll see very different phenomena. We already did in the beginning, because We saw that stellar binary black holes exist because we directly detected them. They form into binary pairs. These binary pairs, we saw it merge, so they merge within the lifetime of our universe. These facts weren't known before. More interesting, they were very heavy. This was totally unexpected from astrophysics, that there would be black holes that are so heavy. The reason is that heavy stars aren't very stable, and so you don't have heavy stars around to make the black holes. In fact, they do exist, so now we have to explain, are there regions of space where heavy black holes can exist because they have low metallicity, for example? Are there other ways that these heavy black holes are made, maybe in dense clusters? Or maybe they're even primordial. So those are puzzles for us to answer. We have technical tools to do that by measuring these black holes mergers much better, seeing lots of examples of them. We can determine effects like the spins, whether they're correlated in the two, and so forth. So that's basically what we've done on the very first events. As was mentioned in the introduction, we have now seen one example of a different kind of phenomenon. It's a binary phenomenon, but it's different. And this was observed last August. It was observed just after we added the third detector to our network, which is the Virgo detector near Pisa in Italy. And soon after that detector was added, we saw a black hole merger together and determined the location much, much better, more than 10 times better than we could with just LIGO alone. Then we saw 2 weeks later the event shown here, which I won't show in detail, but in our case, we measured a new event that lasted minutes, not tenths of seconds in our device. That's because it was very light and was very close. It was not only 100 million light years away. And so we quickly determined that this wasn't black holes. It was actually the merger of two neutron stars. Neutron star is another product of the collapse of a star that isn't heavy enough to make a black hole, but it's different physically. It's nuclear matter, very compressed nuclear matter. Understanding how that nuclear matter works, what happens to nuclear physics under these very extreme conditions, is a big, interesting problem for the future. But as was mentioned in the introductions, this triggered an interesting phenomenon last fall. Our ability to measure is shown where it says first LIGO, not very good, along these long banana-like shapes. A more precise one called LIGO Virgo, that was how well we could determine the position. And within 2 seconds after we made the observation, a satellite that looks for gamma rays from what we call gamma ray bursts saw a signal in the same part of the sky. And you can see that's what says Fermi GBM. That is interesting first in what will follow. It's, for me, interesting in that we've spent 10 or 15 years where astronomers have told us that we can't point well enough to ever work with them, but notice that our position in the sky is better than theirs in this one, so we're very proud of that. Anyway, seeing something that gave electromagnetic radiation and having seen it in a reliable satellite that's been up there for a long time, we were able to basically mobilize the complete astronomical community with many, many instruments looking in different ways. First, of course, gravitational waves. Neutrinos looked but didn't see anything. Visible and infrared light, radio waves, X-rays, gamma rays, and so forth. What came out is this whole history. This shows the signals that we're seeing in different frequencies from electromagnetic radiation. We know where this event happened also, and it was studied in great detail. It is, as was mentioned at the beginning, is the birth of something that we've been anticipating for a long time, and that is what we call multi-messenger astronomy. Astronomy itself has probably, if you attribute one factor to all the advances of the last 50 years, it's the fact that we look at the same phenomenon, or learn to look at the same phenomenon in different frequency bands. So we look at some phenomenon in astronomy, and then we look at the visible, the infrared, the ultraviolet, and so forth and so on. And the combination of all that has enabled us to understand the dynamics of different objects, and I think that's the biggest advance, not one technically in a particular telescope, in astronomy in the last 50 years or so. Now, we talk about not multi-wavelength astronomy, but multi-messenger astronomy, meaning we can use everything, not just electromagnetic radiation. Use neutrinos. We haven't done it yet, but we can. And gravitational waves, as well as all the electromagnetic telescopes that exist in the world. So this is the birth of that subject. What was done fits a picture that had been developed phenomenologically for what happens if two neutron stars collide. So we determined from gravitational waves that what we saw, for reasons that I showed you, was the collision of two neutron stars. But from all the electromagnetic radiation that came out, it tells you all the features of a neutron star collision and fit very well to a model which people like to call a kilonova model, like we have supernova, a kilonova model for the collision of neutron stars, which means looking at all this phenomenal amount of data, one could put it together into such a picture. There's one simple conclusion of this. One simple conclusion, not quite conclusion, one interesting feature of the interpretation of this event is the following, which is the note I want to end on today. And that is we have, and it shows to me that this very abstract science in some way can impact things beyond what you first think it might. We have had a puzzle as scientists understanding how we have heavy elements in nature. So how did gold get in gold mines that you go to, or platinum, or other heavy metals? How did they get there? When we take what we know about the universe, most of the universe is made out of hydrogen and helium. I mentioned that we have stars that are burning. When they're burning, they're using the fusion process. Well, that's making elements up to maybe iron or a little heavier, but basically up to iron. But the heaviest elements don't get made in the fusion process. So how do the heavy elements, how were they made when the Earth was formed? How do we have them in the Earth? And subsequently, you have them on your finger. It's been a puzzle. The best explanation that people had is a phenomenon in nuclear physics called our process, which is that there was an enhanced way somehow in the collapse of a star, like a supernova, to make heavy elements. It's kind of made because you see the heavy elements, and it never was very satisfactory. That's been the main explanation up till we saw this event. How do we make the elements that are in the periodic table? We go into the laboratory and we take heavy elements and we bombard them with lots of neutrons. If we bombard them with neutrons, we make heavier ones. And that's basically how the periodic table has been filled out, by, in laboratories, doing that with neutrons. Now remember, what we have is the collision of two neutron stars. So an obvious projection is that we're doing basically what's been done in the laboratory. You can't really do the phenomenology accurately based on the first and only observation of the collision of two neutron stars, but you can at least make an attempt to do that. And that's been done here. So we don't know that it quantitatively will work right, but it basically has the right features. And that is, in this analysis, the yellow is what is made by the collision of neutron stars in the elements that we have and other processes for the rest. So as you get to the heavy ones, it's almost all yellow. And of course, platinum and gold that we love so much were basically made in neutron star collisions. So it's quite likely that the gold ring that you or your wife or somebody's wearing and love so much, or platinum, was made sometime earlier, of course, in neutron star collisions that we're starting to be able to study. With that, I'll bring this to a close by saying that the field that we're in doing this is really just beginning. And if we reflect back 400 years, Galileo took lenses that were first made because people invented them for glasses, and for the first time made a telescope that pointed at Jupiter. So he pointed a telescope at Jupiter, and he saw 4 moons. And that was the beginning of astronomy, modern astronomy beyond what the naked eye could see. And we've developed incredible tools and spent 400 years developing the astronomy that we have today. What we've done with gravitational waves is in some vague way analogous to the very first telescope. We can barely see gravitational waves at this point. We know we're not limited by nature. We're limited by our own ability to make sensitive enough instruments on the Earth's surface. We know how to make instruments that'll work in space, that'll work in different frequency bands. And in the future, I think we also will know how to make instruments that can maybe look for signals from the early universe. So ask me in another 400 years, and probably we'll know a lot more about the universe. Thank you.
Vamos a abrir un turno de cuestiones, de preguntas. ¿Alguna cuestión? Simplemente levantan el brazo y pulsan el botón que tienen delante, se encenderá la lucecita y podrán plantear cualquier cuestión. ¿Alguna pregunta? Sí, ahí detrás.
You said before in the neutron star merger that the electromagnetic radiation was detected 2 seconds later or something like that. Is there a reason for this?
We see the gravitational effects of the neutron stars coming together. The gamma rays come from the actual nuclear physics when they've merged together. Nobody can say it should be exactly 2 seconds, but 2 seconds later, so it should be later. The first effect is the gravitational merger of these two. Then there's nuclear physics that comes as they merge, the two objects merge together. So it's not surprising that it's a couple seconds later. An interesting point, however, is that these two signals were within 2 seconds of each other, and the object was 100 million light years away. That tells you with pretty good accuracy that gravitational waves are traveling at the same velocity, or almost identically the same velocity as light waves, which is, of course, we only knew theoretically before.
¿Alguna cuestión más? Sí.
Thank you very much, Barish, for this wonderful lecture. You mentioned the clash of Einstein with physical review. on the occasion of these ups and downs, whether gravitational waves were real or not, and an actual effect. That was in the middle of the 30s, true?
Yes.
And my question is in the history of this point well known when Einstein became convinced of the actual existence of gravitational waves? Because at the beginning he predicted in 1916,
Yeah.
but later he was against this. And
So the question is kind of, what do we know about Einstein's history for what he believed in gravitational waves? Obviously, he believed that gravitational waves probably existed in 1916 when he proposed them because they were similar to electromagnetic radiation. In 1936, when he wrote the article first and submitted it to Physical Review letters, or Physical Review, he questioned it. I don't know, he didn't quite decide it wasn't true, he just questioned his. But by the time he actually published the article was published. Yeah, I didn't quite say it right. He pulled the article from Physical Review and said he would never publish there again, and he didn't. Those records I've seen. He resubmitted it to a journal called from the Franklin Institute in Philadelphia. And the title of the resubmitted article was called On Gravitational Waves. They took the article, he resubmitted it there, he first called it that. He fixed the mistakes in the article. And so as far as I can tell, he probably believed that they existed at that point. He had made some mistakes, he worried about it. He believed it. He never returned to the subject again, however. So between 1936 and the 1950s, when he died, he never came back to the subject of gravitational waves.
thank you.
¿Alguna cuestión? Bueno, pues si no hay más cuestiones, sí.
I would like to make to play the devil's advocate for one moment. So, to some extent, this discovery of gravitational waves are the equivalent to the discovery by Hertz of the electromagnetic waves predicted by Maxwell. They both are classical. However, in the case of Hertz, he discovered the electromagnetic waves produced by electric charges, which were already known. But in this case, the discovery is double, in the sense that, to my knowledge, is the first direct observation of a black hole, and at the same time, the gravitational wave. So it's very, very strong statement, the claim, because it is double discovery. So my question is, in order to be totally sure that this corresponds to what it is predicted by theory, how many events like this should be observed, or it is already definitely settled?
So the question can be treated at different levels, but the question that's asked is, how well do we know that what we've seen is gravitational waves from Einstein's formulation of general relativity? We've tested in various ways. I showed you one, but we test in various ways how the signals might differ from Einstein's theory of general relativity, but that's not a very convincing way to determine what's correct. The problem that we have, having been in particle physics myself, where when we look at data from particle physics experiments, we compare one theory with another theory. We're not able to do that here because we don't have other formulations of general. There are alternate formulations of theories of gravity, only they're not developed in the detail that we can actually try to fit our data. So we basically look for, at this point, deviations from Einstein's theory. So we only have the confidence that it fits as well as we're able at the present time. and that when we put in formulations of possible deviations, we don't see them. That's not as satisfying as comparing two alternate theories and seeing which ones give different predictions that we can compare.
Bueno, pues me gustaría agradecer al doctor Barish que haya compartido parte de su precioso tiempo con nosotros y muchísimas gracias por acompañarnos esta tarde, tanto a los que nos han seguido aquí desde el museo como a los que nos han seguido a través de streaming. Me gustaría recordarles que esta noche a las 10 de la noche ofrecemos también el programa Berkeley on the Big Screen, que es gratuito hasta completar el aforo, y aquellos de ustedes que estén interesados, informarles que también el jueves pues tendremos otra sesión. Muchísimas gracias y les pido un fuerte aplauso por esta magnífica conferencia. Muchas gracias.